The second instruction of video and energy and momentum is on the conservation of momentum. In conservation momentum type problems, you're going to either deal with collisions or explosions. We'll start with collisions. A collision problem could look like two cars crashing into each other. It could look like a satellite crashing with an asteroid in outer space. Sports has a lot of collisions. A linebacker tackling a running back in football. A baseball bat hitting a baseball. It could be a player checking another player in hockey. So sports offers a lot of collision type problems. Explosions could be things like a stick of dynamite, a firecracker, a grenade. But that also incorporates things such as like a gun firing a bullet. This is considered an explosion because before the gun fires the bullet, you have the gun and bullet together as one object. Once the trigger is pulled, the bullet and the gun become separate. So no, it's not an explosion, say like a grenade going off, where you're going to get thousands of pieces of shrapnel. Instead, it is a much more controlled explosion in which you had one object and now you have two. And the same thing can apply for a tank firing a cannon or a cannon firing a cannonball. Sports also offers explosion type problems. It's a little bit stranger to think about, but for example, in baseball, as a pitcher throws a pitch, it's technically an explosion type problem. You originally had the ball and the player together as one object. Then as the ball is thrown, you now have two objects that are separate from each other, the baseball and the pitcher. Whether it be collision or explosion, the whole idea is momentum is conserved. So whatever the momentum was before the event occurred equals a momentum after the event occurs. So in a car crash, we look at the momentum of one car, and we look at the momentum of the second car. Whatever the momentum is of those two cars combined before they crash, once they smash into each other and become one object, or if they bounce off of each other and still remain two separate objects, the momentum is going to be conserved. If we're talking about an explosion, say a grenade or a firecracker, if it's just sitting there, say a firecracker is placed on the ground and just sits there and has no momentum because it's not moving, when it explodes, all the thousands of pieces that it explodes into, when you add up all their momentums together, it should still equal 0. So this can apply for any type of the problems we took a look at: a satellite and a meteor, a gun and a bullet, a tank and a shell, car crash, and so on and so forth. So what is the same and what is different? Because here's where it gets tricky. First off, let's take a look at what momentum is. Momentum is abbreviated by the letter P, and momentum equals mass times velocity. So momentum is mv. When we say momentum is conserved, we mean the mass times velocity, say an example of a car crash, the mass times velocity of the first car, plus the mass times velocity of the second car, added together is the total momentum. After the car crash, the mass plus velocity of the first car after the crash, added to the mass times velocity of the second car after the crash, are going to be equal to each other. So momentum before equals momentum after. But there's more to this though, because the other thing to take a look at is impulse. Impulse is J. I understand that's a little strange. You would think it might be a capital I, but for one reason or another it got the label J. Impulse is force times time. That's also known as mass times the change in velocity. I can't do a delta sign right now, but do know that this is a change in velocity, not velocity. So impulse is force times time, also known as mass times change in velocity. So two objects crash together. What things do they share? The change in momentum of each object is the same. So if object A is a car and it crashes into object B, another car, if object A has gained momentum in some way, therefore object B had to have lost the momentum, because momentum is conserved. But the quantity of momentum gained by object A has to equal the quantity of momentum lost by object B. We know back in the force unit that Newton's third law tells us they both experience the same force in any kind of one object hitting another. They will both have to experience the same impulse because the duration of the impact has to be the same time. So once again, impulse is force times time. Newton's third law tells us they have the same amount of force exerted on each other. The time has to be the same. You couldn't possibly be touching an object without it touching you. Therefore, the impulse has to be the same. What is different in a crash? Because this is what seems to cause problems. If we were to take, for example, a train smashes into a car that was stuck on the tracks, most people are going to say, oh, that car had a much bigger change of momentum, or that car exerted or had a bigger force exerted on it. But both of those statements are false. What we're getting confused with is the things that are different are the accelerations and the changes in velocities. So if we think train smashes into car, the car experiences a greater acceleration because it has a smaller mass. The train experiences a smaller acceleration because it has a much greater mass. That greater acceleration the car experiences results in a greater change in velocity than the train would experience because the train has a much smaller acceleration due to its large mass. But keep in mind, Newton's third law says train smashes into car, experiences the same force. Therefore, train smashing into car is going to be the same change in momentum. What is different is the change in velocity. The car will have a much greater change in velocity. We can even make this more extreme. A train smashes into a fly. Both the train and fly experience the same force exerted on them. Because the time of the impact is the same, they experience the same impulse and experience the same change in momentum. The train, though, is more massive, so therefore it's going to experience a much smaller acceleration and therefore a much smaller change in velocity. That's all I have. Thank you for watching.